The James Webb Space Telescope launched in 2022. The first images arrived, and scientists couldn't believe what they were seeing, because there was something there that shouldn't have been. In the oldest corner of the universe, when it was only 290 million years old, massive galaxies were sitting there. Old, large, structures harboring billions of stars. Physics didn't allow for this. Not a single equation in cosmology had predicted it. And this video will walk you through, step by step, why that prediction fell apart when the universe was only 290 million years old. Galaxies that should have taken billions of years to form were already there. This wasn't just unexpected. This was a finding that shook 80 years of cosmological modeling to its foundations. But the real issue was something different. The real issue was what was inside these galaxies, because they weren't just large. Inside them were elements that should have taken billions of years to form. How? To understand this, you first need to know how the universe began, and what you think you know is probably not entirely correct. Most people imagine the Big Bang as an explosion. Matter was scattered from a single point and the universe expanded. That's wrong. The Big Bang was not an explosion. It was the expansion of space itself. Every point, simultaneously, grew in every direction. This isn't actually hard to picture. Think of it this way. Imagine a balloon with dots on it. As you inflate the balloon, every dot moves away from every other dot, but no dot is at the center. They're all moving away from each other at the same time. The universe expands exactly like this. And that expansion is still happening right now, this very second. In 1929, Edwin Hubble discovered that galaxies were moving away from each other. If you rewind, you see that everything was once together in a single point. In 1965, Arno Penzias and Robert Wilson detected a uniform heat signal coming from every direction in the universe. This was a residual temperature left over from the Big Bang, like the warmth left in the ashes of an extinguished fire. Both received the Nobel Prize. The model was solid, and according to this model, the universe is 13.8 billion years old. Why does this number matter? Because it sets a limit on everything. Nothing can be older than 13.8 billion years. Large galaxies need billions of years to form. Our own galaxy, the Milky Way, took 10 billion years to reach its current form. The solar system didn't begin forming until the universe was already 9 billion years old. Webb shattered this calculation. But wait, how can Webb see so far? There's fundamental physics at play here. The universe is expanding. As a galaxy moves away from us, the wavelength of the light coming from it stretches. Just like the siren of an ambulance driving away gradually drops in pitch, visible light shifts into the infrared. Light from a sufficiently distant source moves entirely out of the visible spectrum. Hubble couldn't see this. Webb can. Webb is sensitive to infrared light. This makes it, in the truest sense, a time machine. The farther you look, the further back in time you're seeing. Light from a galaxy 13 billion light years away left 13 billion years ago. When Webb captures that light, it sees that galaxy exactly as it was at that moment. A genuine window into the past. But sending Webb into space was itself a miracle. And without knowing this story, you can't fully appreciate the weight of its discoveries. The telescope was so large it had to be launched, folded up. It consists of 18 hexagonal mirror segments. Each segment needed to align with the others with millimetric precision. In space, automatically, it unfolded in a single sequence. This unfolding process took 2 weeks. Every step was critical. Every mechanism was vital. If a single thing had gone wrong, the telescope would have been useless. And no one could go to repair it. Webb is 1.5 million kilometers from Earth. The space shuttle could go to repair Hubble. There's no such chance with Webb. No crewed vehicle can reach it. Also, infrared observation requires being cold. If the detectors warm up, their own thermal noise would drown out the most distant light in the universe. Webb carries a 5-layer sunshield the size of a tennis court. The shaded side drops to -233 degrees, only 40 degrees above absolute zero. Finally, the telescope was anchored at the L2 Lagrange point. At this point, the Sun, Earth, and Moon always remain on the same side of the telescope. Observations are continuous and uninterrupted. If all of this works correctly, Webb can peer into the darkest corners of the universe. And it did. The JADES program is Webb's Deep Universe Survey Campaign. Full name: James Webb Space Telescope. Advanced Deep Extragalactic Survey. Hundreds of hours of observation. Depths even Hubble couldn't reach. And in this survey, JADESGSZ140 was found. This galaxy existed only 290 million years after the Big Bang. Earth is 4.5 billion years old. This galaxy was already there 13.5 billion years before Earth existed, when the universe was still an infant. It's hard to imagine that era. Stars were only just beginning to form. The period called the Dark Ages, that universe where light barely existed, had only just ended. In a universe that had just awakened, this galaxy had emerged, grown, and matured. And it wasn't just there. It was large, unexpectedly large. It harbored billions of stars, and those stars were not young. Pay attention now. This is where the real problem begins. Heavy elements are formed when massive stars explode. Carbon, oxygen, iron. These didn't exist in the Big Bang. In the early universe, only hydrogen and helium existed. Heavy elements are produced inside stars. When those stars explode, they scatter into space. The next generation of stars is born from those remnants. This galaxy had those elements, which means this galaxy formed, produced stars. Those stars matured, exploded, and died, and new stars were born from the remnants. This entire cycle had been completed in just 290 million years. The model did not predict this, and this was not a single exception. Webb began finding similar galaxies, one after another, from periods when the universe was far younger, structures far larger than expected. What does a redshift value mean? The faster a galaxy is moving away from us, the more its light shifts toward the red. A Z equals 14 value means the wavelength of light from that galaxy has stretched by a factor of 15. This shows that the galaxy existed when the universe was only a few % of its current age. Webb found galaxies at Z equals 10, Z equals 12, even Z equals 14. All larger than expected, all more mature than expected. NASA's researchers searched for errors. A calibration problem? A data processing error? A distortion from the telescope itself? Perhaps the redshift values had been miscalculated. Perhaps the masses of the galaxies were being overestimated. They checked repeatedly. There was no error. Cosmologist Mike Boylan-Colchin from the University of Texas wrote in a research paper, "These objects should not exist." A scientist rarely says this. They say unexpected. They say surprising. They don't say should not exist, but he said it. And that single sentence summarized the dead end modern cosmology had found itself in. So what's happening? The scientific community is currently debating 4 possibilities, and each one is revolutionary in its own right. First, the standard model is incomplete. The Lambda CDM model explains the large-scale structure of the universe. It describes how dark matter, dark energy, and ordinary matter interact. But perhaps there's a gap in this model that fails to account for galaxy formation being this rapid in the early universe. Some parameters of the model may be incorrectly calibrated. This is the most moderate explanation, not discarding the model, but fine-tuning it. The second is more unsettling. Dark matter may be behaving differently. The invisible halo of matter surrounding galaxies triggers star formation. Dark matter clusters first, draws in ordinary matter, and galaxies take shape at those gravitational centers. If this matter was distributed very differently in the early universe, galaxies could have formed at incredible speed. Some physicists argue that dark matter took a different form in the early universe than it does today. The first stars were very different. The very first stars of the universe have never been observed. They are known as population 3 stars. According to theories, they may have been hundreds or even thousands of times larger than the Sunday. Such stars live and die very quickly, hundreds of thousands of years, not millions. If these giants formed in far greater numbers than predicted and died rapidly, galaxy formation could have accelerated dramatically. Webb is also searching for these first-generation stars. This search itself stands on the threshold of a historic discovery. The fourth is the most staggering possibility. One of the fundamental parameters of the Big Bang model may be wrong. Two different methods for measuring the expansion rate of the universe are producing conflicting results. This is called the Hubble tension. One method says the universe is expanding faster, the other says slower. The difference between the two seems small, but the implications are enormous. Webb did not resolve this conflict. It deepened it. If the expansion rate of the universe has been measured incorrectly, its age may have been calculated incorrectly as well. And then everything changes. 13.8 billion years may not be right. All the calculations would need to be redone. Pause for a moment. Why is this not just a problem for scientists? The Big Bang model is not only the foundation of cosmology, nuclear physics, particle physics, the concept of time. All of it is built on this framework. Once in history, a moment like this occurred. Newtonian physics worked for centuries. Planets moved in their orbits. Apples fell. Everything was predictable. Scientists had begun to think physics is complete, until Einstein redefined gravity as the curvature of space-time. Newton wasn't wrong. He was incomplete. At high speeds, with large masses, the model broke down, and without Einstein's correction, GPS would not work. The timing of satellite signals has to be calculated according to the curvature of space-time. If calculated with Newtonian physics, several kilometers of error would accumulate each day, and the system would be useless. The phone in your pocket, your car's navigation, aircraft guidance systems, all of it depends on Einstein's correction. Perhaps what's happening now is similar. The Big Bang model is not wrong, but it cannot fully explain galaxy formation in the early universe. And Webb brought this gap to light, just as Einstein made visible what Newton couldn't see. So what comes next? Webb is still observing. The JADES program continues. With every new observation period, it looks farther and further back. Scientists are searching for galaxies at Z equals 15, Z equals 16. If structures from just 200 million years after the Big Bang are detected, the debate will intensify dramatically. Some researchers believe this is possible. At the same time, theorists are working to update their models. Different distribution scenarios for dark matter are being calculated. Simulations of early star formation are being redone. Webb's data is reaching more research groups with each passing month. Where will this research lead? 95% of the universe is still dark. Dark matter, dark energy. We can't see it. We can't measure it. We don't fully understand it. Everything we can see, all the stars, galaxies, planets, you, me, is only 5%. The rest is, in the fullest sense of the word, unknown. Without understanding them, we cannot fully grasp how stars die, how galaxies evolve, or even the distant future of our own solar system. Webb is shining a light on this darkness, in both the figurative and the literal sense. For thousands of years, humanity looked up at the sky. The universe turned out to be larger than we thought. Each time, what we knew about ourselves changed. And now Webb is telling us this: the universe, from its very beginning, has been working very differently than we predicted. From its very first moments, something was unfolding differently than we imagined. We could only see this now when we built this telescope. We built the tool needed to ask the question. We asked the question. The answer surprised us. That is exactly what is supposed to happen. happen. If you found this video valuable, you can hit the like button. You can use the button below to subscribe and write in the comments what kind of content you'd like to see.